All right, let's talk piecewise functions. Piecewise functions, remember, are functions that have subfunctions or think they follow different expressions on different intervals of the domain. So when you look at a piecewise function, the left side, remember, represents the intervals of the domain, and then the right side, or the left side, are the expressions or kind of the subfunctions that each of the different intervals follows. So to check or to evaluate a piecewise function algebraically, you look at your input and then see which interval that particular input falls in and then evaluate it. So if I go to f of negative 1 falls in my second interval from negative 5 up to and including 0. So it follows the rule of x squared minus 3x, and we know evaluating it, we're just going to substitute that in. So it gets me negative 1 squared minus 3 times negative 1. Negative 1 squared is a positive 1. 3 times negative 1 is negative 3. Minus minus becomes a plus. So 1 plus 3 is 4. Next one, f of 4. So 4 falls in my bottom interval because 4 is greater than 0. So it's going to follow x to the 4th minus 7. So that gets me 4 to the 4th minus 7. 4 to the 4th power, 4 times 4 times 4 times 4 gets me 256 minus 7. Doing that subtraction, 249. Next one, f of negative 10. So negative 10 is going to fall in my first interval because negative 10 is less than negative 5. So I'm going to substitute that in for x. So 3 over negative 10 plus 4. If I simplify that denominator, negative 10 plus 4 is negative 6. So that gets me 3 over negative 6, which I know finally reduces down to negative 1 half. And finally, f of 0. That is going to be in my middle interval because specifically this piecewise function is defined. That second interval in the middle is up to and including 0. So it's going to follow that. So 0 squared minus 3 times 0, and all of that gets me a final result of 0. Remember, when you're looking at those, just to see kind of the endpoints and see which interval they fall in, because sometimes that's a mistake that people will make. Okay, let's talk about the graph. Let's look at this one, like this one. So remember, piecewise functions, they look kind of weird on the graph just because there's a lot of different rules and expressions going on, but we don't read it any differently. Okay, so we know again our input, our x coordinate is going to be in parentheses. So I'm going to look on my graph and see at 3, at an x coordinate of 3, what's my y? So x is 3 here, y is 2, so f of 3 is 2. You just take a look at the graph and see where it falls. Okay. All right, if I do f of negative 1, so I go my x is negative 1. I see two values. One's a whole, one's a closed circle. Remember that the whole represents that that x coordinate or that x value is not defined there. So that piece of the domain is not defined there. The closed circle is where it is defined. So f of negative 1 is not 3. It's where the closed circle is, which is looking at about roughly in between 2 and 3, about 2.5. So about 5 halves, roughly. I'm going to put approximately 5 halves. Negative 5 halves also. So it's going to be approximately negative 5 halves. Okay. On my next one, I have f of negative 3. So my x is negative 3. My y is also negative 3. When I have f of 2, that's easy. That point is right there. F of 2 is going to be a positive 1. And then f of 0.5 or f of 1 half, let's go partially between 0 and 1. That is roughly right here, and on my graph falls about there, so that gets me 2. So remember, that's how you read the graph of a piecewise function, and then just looking and seeing again the difference of when it's defined versus when it's not defined. Okay, so now let's go ahead, let's talk about graphing and all the different pieces of information that we talked about. Domain, range, intercepts, all that. So remember, you're just kind of graphing the lines or the functions on the different pieces of the domain. Okay, so this is where remembering how to graph linear functions and lines in general comes into handy. So if I'm looking at this first example, I have 2x plus 3 on the domain up until and including 0. So I can think, again, I have a slope of 2, I have a y-intercept of 3. So I can go ahead and I can plot that because my domain, this interval of my domain, is up to and including 0. So if I substitute 0 in for x, that gets me a value of 3. So I know the point 0, 3 is on there. So I'm going to go 0, 1, 2, 3, that point right there. Okay. Now if we think we have a slope of 2, this is kind of just remembering how you graph lines. So slope of 2, I can go down 2 to the left 1 because negative over negative makes a positive. And same thing, down 1, 2 over 1, down 1, 2 over 1, down 1, 2 over 1, 1, 2, 1. So again, this is just me graphing this line. I'm plotting all these points just to try to be as specific as I can. So there's that there. Okay. And now let's do my next line, which is 1/2 x minus 1. Let's mark this. This is first line. Okay. 1/2 x minus 1. So I have a slope of 1/2 and a y-intercept of -1. But it's not defined at 0. So when I plot that point 0, -1, I need to make sure that I put the whole, just because it's not defined there, but it picks up right after 0 on that new rule. So now we have a slope of 1/2. So positive 1/2, so I can just go up 1 over 2, up 1 over 1, 2, up 1 over 1, 2, up 1 over 1, 2, 1, 1, 2. And then that's just going to keep on going in that direction, okay? Big important piece is making sure that you put those arrows, because if you don't put the arrows, then you're saying that the function stops at those different pieces of the domain, and it does, again, just keep on going. So it is important that you put the arrows. So domain range, again, we can kind of take a look at the graph. The domain, it has no it has no break, number one. It's defined on all real numbers, so this is going to be -infinity to infinity. And then if I look at my range on my y-axis, it is going to just continue to also be from -infinity to +infinity. Okay. All right, let's now talk how we find x-intercepts. Remember, to find x-intercepts algebraically, you set your equation or your function equal to 0. So to check it for piecewise, you need to set each individual piece equal to 0, solve for x, and then check, is that x value actually in the interval of that domain? Okay, so if I check my first one, we'll do 2x plus 3 equals 0. So I'm going to solve this for x, so subtract 3, so 2x is going to be -3, and then x is going to be -3/2. So I take a look now at my interval. -3/2 is less than or equal to 0, so that is a x-intercept that I have. So that -3/2, 0, is an x-intercept. And I also want to check my other one. So I want to do 1/2 x minus 1, set that equal to 0. So I'm going to add 1, so 1/2 x equals 1. And then to get rid of that 1/2, remember we're going to multiply by the reciprocal, 2 over 1, which is just 2. So x is going to be 2. And now I check 2 is greater than 0, so that is a second x-intercept, 2, 0. So that's my x-intercepts. And now if I go to my y-intercept, remember that is where I plug in 0. So 0 is defined on the first interval of my domain. So I can just go ahead and do 2 times 0 plus 3. And then that is equal to 3. So the y-intercept of this graph is 0, 3. And you can also kind of take a look at that by just looking at the graph. And last question, continuous or discontinuous. There is a break. There's a gap in the graph, so this would be an example of a discontinuous function.